How do models learn? Traditional forecasting models learn from one series, then predict its future, but time series foundation models are different. They are trained on massive collections of many time series from many domains. Because they see so much data, they can forecast new series without retraining, also known as zero-shot forecasting. That is powerful, sexy, and very tempting to businesses, but it creates a problem. If a model has already seen patterns related to the test data during training, evaluation scores may look better than they should, and let's be honest, given that the model creators have scraped everything online, all the benchmarks are in the training data. This is the point this new paper is making. Current benchmarks may measure memorization rather than real forecasting ability. Figure 1 compares 3 ways to evaluate forecasting models. The first approach is time cross-validation. You train on earlier observations of a series and test on later ones, rolling forward in time. The second approach tests across many different series, each with one trained test split. This is common in TSFM benchmarks because these models aim to generalize across domains. The third approach combines both ideas, many series and multiple time splits. This combined method provides a more stable picture of model performance, though it is still not widely used. The fact it's tricky to implement properly might have something to do with that. Section 3 of the paper introduces the core argument. The authors identify 2 ways information can leak into evaluation. The first is direct leakage. A dataset used in training might later appear as a benchmark test set. With large and reused repositories, this happens way more often than expected. The second is indirect leakage. Even if the test series was never seen before, another correlated series may have been observed during the same time period. Because TSFMs learn statistical patterns, they can transfer these shared signals and appear to forecast well. Figure 3 explains indirect leakage with a simple idea. Imagine 2 time series driven by the same external event. One could be a stock index in Germany and the other a stock index in the US. If a model trains on the German series during the COVID crash, it learns the shape of that event. Later, when asked to forecast the US index over the same period, it can reproduce the crash pattern. The model never saw the US series directly, yet it still carries information about that event. This violates the independence expected in a fair test. Section 4 shifts from diagnosis to solutions. The authors argue that leakage occurs along 2 axes. One is the sample dimension, meaning which datasets appear in training and testing. The other is the temporal dimension, meaning when observations were collected. Even if datasets differ, overlapping time periods can still leak information through shared events. The key message is that evaluating TSFMs requires rules that handle both dimensions simultaneously. Otherwise, benchmarks may reward models that remember past signals instead of models that truly predict unseen data. Figure 5 summarizes the framework proposed in the paper. At the top are the strengths of TSFMs: large, diverse data, global pattern learning, and zero-shot prediction. Below that are the 2 leakage risks. Direct leakage occurs when training and test datasets overlap. Indirect leakage occurs when correlated series share the same time period. The figure then shows 2 requirements. First, benchmarks should allow any training data but ensure test data is truly new. Second, test periods must start after the latest training time used by any model in the comparison. The paper warns that TSFM evaluation may repeat problems seen with large language models. When models train on massive datasets, ensuring that evaluation data is independent becomes difficult. The authors show 2 key leakage mechanisms: dataset reuse and temporal overlap between correlated series. Both can inflate reported performance. To avoid this, benchmarks should allow flexible training but enforce strict test periods that occur after all training data. With these rules, evaluation would better measure real forecasting ability rather than pattern recall.